Morning. Okay, in the last class, we discussed about the extraction of signal from noise by correlation, and this is another technique that is extraction of signal from noise by filtering. Okay, a signal masked by noise can be detected by correlation technique or by filtering. These are the two techniques. These two techniques are equivalent. One is used in time domain and another one is used in frequency domain. So correlation technique is means of extraction of the signal in the time domain, whereas filtering is exactly same result in the frequency domain. So we'll see the relation between these two. So relation between correlation and filtering. So consider the two arbitrary signals f1 of t and f2 of t. So the cross correlation function j12 of tau is defined as Fourier transform of f1 of t is f1 of omega, and Fourier transform of f2 of t is f2 of omega. Then Fourier transform j12 of tau is nothing but multiplication of f1 of omega into f2 of minus omega, right? So cross correlation in the time domain and frequency domain is like this. So consider these two diagrams. So this is cross correlation function. Here input is f1. This is the this is the another function f2 of t. So j1 of w is nothing but cross correlation of f1 of t and f2 of t. So here coming to this is in time domain. This is in frequency domain. Coming to the frequency domain, a the transformation of f1 of t is f1 of omega, transformation of f2 of minus t is f2 of minus omega. So product of these two is f1 of omega into f2 of minus omega. This is nothing but this is the correlation, cross correlation frequency domain. So the impulse response h of t of a system with a transfer function f2 of minus omega is given by h of t is nothing but inverse Fourier transform of f2 of minus omega. But f2 of t is Fourier transform of f2 of t is f2 of omega, and Fourier transform of f2 of minus t is f2 of minus omega. Hence, h of t is f2 of minus t. See here, h of t is f2 of minus t. So this result can now be applied to the problem of the detection of the periodic signal from the random noise signal. So let s of t and n of t are the periodic component and random noise components. Respectively, s of t is the periodic component and n of t is the random component. Okay, then the received signal f of t is nothing but sum of the periodic signal and noise signal, right? So that is s of t plus n of t. So the periodic component s of t present in f of t can be detected by cross correlating f of t with another periodic signal c of t. So here f of t is mixed with the periodic signal and noise signal. So this f of t is correlated with another periodic signal c of t of the same period as that of s of t. Okay, so we need a system which has unit impulse response c of minus t or which has a transfer function c of minus omega, where the Fourier transform of c of t is c of omega and Fourier transform of c of minus t is c of minus omega, right? So C of t is a periodic signal of period t naught, whereas C of omega is the Fourier transform of C of t, which will consist of impulses located at omega equal to 0 plus or minus omega naught plus or minus 2 omega naught plus or minus m omega naught, where omega naught equal to 2 pi by t naught. So these impulses have magnitudes equal to 2 pi times the corresponding quotients of the exponential Fourier series for C of minus t. Thus, if C of t is expanded by Fourier series, then C of t can be expressed as sigma n equal to minus infinity to infinity Cn into e power plus jn omega naught t, where omega naught equal to 2 pi by t naught. Then Fourier transform C of omega of C of t is given by C of omega equal to 2 pi into sigma n Cn into delta of omega minus n omega naught, whereas e of e power gn omega naught t can be replaced by delta of omega minus n omega naught. Since c of minus omega is nothing but c star of omega, then c of minus omega equal to 2 pi into sigma n cn star of cn star into delta of omega minus n omega naught. Thus, c of minus omega consists of impulses located at omega equal to 0 plus or minus omega naught plus or minus 2 omega naught, etc. So C of minus omega represents a system which attenuates all the frequencies except at omega equal to 0 plus or minus omega naught plus or minus 2 omega naught and up to plus or minus n omega naught. So let us consider C of t be a sinusoidal signal cos omega naught t and let the cross correlation be performed over a finite interval. Then from minus t to minus t naught to 0, which is as shown as, so minus t naught to 0, it is C of t. C of minus t is its mirror image 0 to t. Okay, then C of minus omega is nothing but this one. So it is varying from minus omega naught to plus omega naught. Okay, so the Fourier transform of C of minus t is a sampling function shifted by plus or minus omega naught. So figure C is the magnitude function. This is nothing but the magnitude function of C of minus t. Okay, that is C of minus omega. C of minus omega versus omega can be drawn like this. Okay, this is about the correlation, cross correlation, auto correlation, its properties. Okay, next detection of periodic signal by from correlation and filtering. Okay, relation between correlation and filtering. Okay, all we discussed in our earlier classes. Now we are going to discuss about the sampling theorem. Sampling theorem. Okay, right. So sampling, what is meant by sampling? Sampling is a process of converting continuous time signal into discrete time signal. So continuous time signal is always continuous for all time t. So how to get a discrete time signal from continuous time signal? So this continuous time signal can be frozen for some time and it can be divided into equal intervals of the time. That is nothing but a discrete time signal. So it is nothing but the process of, it is nothing but the sampling process. So sampling process is nothing but the process of converting a continuous time signal into discrete time signal. Okay, after sampling, the signal is defined at a discrete instance of time and the time interval between two subsequent sampling instances is called sampling interval. It is very small value. Sampling interval is very small value when compared to the time period of the continuous time signal, right? So after the sampling, the signal is defined at discrete instance of time and the time interval between the two subsequent sampling instants is called sampling interval. Here, one of the important factors is the signal sampling rate must be kept sufficiently high. So here, the signal sampling rate must be kept sufficiently high so that the original signal can be reconstructed from its samples. Okay, so that we have kept the sampling signal rate very high. Okay, so it is represented diagrammatically as like this. Here, f of s, x of t is the input signal. Okay, so f of s equal 1 by t, sampling frequency that is 1 by t, the switch is on, then we will get x of n, x of n equal to x of n. This is the sampled sequence. This is the sampled sequence of x of t, right? Or we can define it as figure b, that is x of t is multiplied with the train of impulses, that is delta t of t. So we will get the x of n signal sample sequence of x of t is like this. Okay, train of impulses. X of t multiplied by train of impulses, that is delta t of t. Okay, that is sampling operation. So here capital T is nothing but the time interval between successive samples, and the sampling frequency of x is reciprocal of the time interval, that is 1 by t hertz. So another way of representing the discrete time signal is x of s, excess of t. Excess of t equal to x of t multiplied by delta t of t, that is train of impulses. Input is multiplied by train of impulses. Let it be considered as equation number 1, where delta t of t is equal to sigma n equal to minus infinity to infinity delta of t minus nt, delta of t minus nt, that is equation number 2. Delta t of t equal to sigma n equal to minus infinity to infinity delta of t minus nt. So that is the function excess of t is the product of x of t and the train of impulses. So that is excess of t equal to sigma n equal to minus infinity infinity x of nt into delta of t minus nt. That is equation number 3. Applying Fourier transform to equation number 3, we get Fourier transform of excess of t is equal to Fourier transform sigma n equal to minus infinity to infinity x of nt into delta of t minus nt. That is nothing but we will extract this delta of sigma n equal minus infinity infinity x of nt into Fourier. transform delta of t minus nt, that is equation number 4. But we have Fourier transform delta of t minus nt is nothing but integral minus infinity to infinity delta of t minus nt into e power minus j omega t dt, right? So it is nothing but e power minus j n omega t. That is equation number 5. So therefore x of e power j omega is nothing but Fourier transform of xs of t is equal to sigma n equal to minus infinity to infinity x of nt into e power minus j n omega t. That is equation number 6. Okay, but we know that the delta t of t is nothing but sigma n equal to minus infinity to infinity delta of t minus nt, that is equal to 1 by t into sigma m is minus infinity infinity e power jm omega naught t. Let it be considered as equation number 7, where omega naught is 2 pi by t or 2 pi f. Okay, now excess of t is equal to x of t multiplied by delta t of t, that is 1 by t into sigma m is minus infinity infinity e power j omega naught t, that is equal to 1 by t into sigma m equal to minus infinity infinity x of t into e power j m omega naught t, that is equation number 8. So therefore Fourier transform of excess of t is equal to 1 by t into sigma m is minus infinity infinity Fourier transform of x of t into e power j m omega naught t, that is equation number 9. If Fourier transform of x of t is x of j omega, then Fourier transform of x of t into e power j m omega naught t is equal to x of j omega minus j m omega naught. That is equation number 10. By substituting equations 10 in equation 9, we get yeah, for a Fourier transform of excess of t is equal to 1 by t into sigma m is minus infinity to infinity x of j omega minus m omega naught, r is equal to 1 by t into sigma m is minus infinity to infinity x of j omega minus omega naught is 2 omega naught is 2 pi by t, that is 2 pi m by t. That is equation number 12. Therefore, thus the Fourier transform of the sample signal is given by an infinite sum of shifted replicas of the Fourier transform of the original signal. Okay, so the Fourier transform of the sample signal, that is excess of t, is given by an infinite sum, that is m is varying from minus infinity to infinity. Okay, sum of shifted replicas of the Fourier transform. So it is clearly here the replicas are shifting. So that is a j sigma minus 2 pi m by t. Okay, shifted replicas of the Fourier transform of the original signal. Okay, so that is about the sampling theorem. This is nothing but the sampling theorem. Okay, now consider the signal x of t is band limited to fm, that is the highest frequency component of x of t is fm. Then x of j omega is equal to 0 for mod omega is greater than omega n, where omega n is 2 pi fm. Okay, that is equation number 13. So it can be represented diagrammatically as x of j omega is varying from minus omega m to plus omega m. Okay, minus omega m to plus omega m. So that is frequency spectrum of continuous time signal. Yes. So x of j omega equal 0 for mod sigma mod omega is greater than omega m, where omega m is 2 pi fm, that is equation number 13. So x of j omega is represented like this. It is varying from minus omega m to plus omega m. It is the frequency spectrum of continuous time signal, and the frequency spectrum of x of nt with pi by t equal to omega m is like this. It is expanded like this. Pi by t is equal to omega n. If pi by t is omega n, that is excess of j omega versus omega can be represented like this. Then if pi by t is greater than omega n and less than omega n, then it will be represented like this. If pi by t is greater than omega n, then it will be represented like this. It can be expanded like it is spreading from minus 2 pi by t to plus 2 pi by t. Here pi by t is greater than omega n. If pi by t is less than omega n, it is represented like this. So minus omega m to omega m and 2 pi by t to plus minus 2 pi by t to plus 2 pi by t is represented like this. So here we will get the Eliason error. Eliason. This is called the intersection of these two samples. So this is called Eliason. So here Eliason occurs in the above diagram. We can prevent the Eliason error with the highest frequency component omega m and the signal x of t is less than or equal to pi by t. Okay. So omega m is less than or equal to pi by t. If the condition omega m is less than or equal to pi by t, then we can prevent the aliasing error. Okay. So omega m is less than or equal to pi by t. Okay. So if sampling frequency fs equal to 1 by t, then pi into fs is greater than or equal to omega m. Here, the condition pi by t is greater than or equal to omega m, then only we can prevent the aliasing error. So pi by t can be represented as pi into fs is greater than or equal to omega m. Pi fs is 2 pi into fm, right? Omega m is 2 pi fm, or pi gets cancelled. So fs is greater than or equal to 2 fm. That is equation number 14. So fs is greater than or equal to 2 fm. Okay. So this is the condition. This is the condition for the sampling theorem. If the sampling frequency is greater than or equal to double the maximum frequency, highest frequency component present in the signal. So it is defined. The definition of the sampling theorem is like this: a filter, a band limited signal x of t with x of j omega equal to 0 for mod omega is greater than omega m is uniquely determined from its samples x of nt if the sampling frequency fs is greater than or equal to 2fm. That is, the sampling frequency must be at least twice the highest frequency present in the signal. Okay, so that is the definition of the sampling theorem. We have to write the sampling theorem like this only. Okay, so that is defined as a band limited signal x of t with x of j omega is equal to 0 for mod omega is greater than omega m is uniquely determined from its samples x of nt if the sampling frequency fs is greater than or equal to double the highest frequency component present in the signal. That is, sampling frequency fs must be at least twice the highest frequency present in the signal. That is, fs is greater than or equal to 2fm. Here the signal will be band limited signal. X of j omega equal to 0 and mod omega is greater than omega m is uniquely determined from its samples x of nt and the condition f of s is greater than or equal to 2fm. This is nothing but the sampling theorem. With this, I am concluding the today's class. Next class we will discuss about the Nyquist rate. Okay, Nyquist rate is anti-aliasing filters, signal reconstruction, etc.